Welcome. This is the regression analysis course. My name is Nicoleta Serban. I'm an associate professor in the School of Industrial System Engineering. The topic of this lesson is the implementation of statistical inference with a data example, and I'm going to illustrate that example using the R statistical software. We're going to use the second example where we're interested in a variation in the mean SAT score, and we'll learn how to include controlling factors and explanatory factors in a model. This is a set of questions we may want to address in statistical inference. What is the estimate of the coefficient of beta 1 or other coefficients and its variance? And we may want to obtain its sampling distribution. Is this coefficient statistically significant? And we can draw this conclusion based on a p-value. What is the F statistic for the overall regression? And do we reject the null hypothesis that all regression coefficients are 0? We may want to obtain the 90% confidence interval for beta 1, as well as we may want to see whether adding to the controlling factors, x1 and x6 in this case, adding other explanatory factors will have a predictive power and will improve the predictive power of the regression model. So this is the output for performing the linear regression model for this particular example. In this example, we're going to read the SAT data. This data has a header, so the columns have names. We use the function, the command attach, in order for R to use the columns in this data as individual objects. And the regression command, again, we're going to use LM. On the left, we're using the response variable, which is SAT, and on the right, we're adding the predictive variables. Takers rank, the first two, corresponds to the controlling factors. I move them to be the first, to enter the model first. Then I'm adding the other four: income, years, public, and expenditure. And this is a portion of the summary of this estimated regression model. What we see here, again, we have information about estimated regression coefficients, their standard errors, t-value, and the probability of the statistical significance test. So we're interested particularly in the first predictor, takers, and the estimated coefficient is minus 0.48, and the standard error is 0.693, and the t-distribution has the sampling distribution. It has a t-distribution with 43 degrees of freedom. If you remember, 43 corresponds to n minus p minus 1. If we want to test for statistical significance, we can use information about the p-value in this output. The p-value is greater than 0.1, which means that we do not reject the null hypothesis that the coefficient corresponding to this predictor is 0. However, if you remember, this is one of the controlling factors, and we would expect that this predictor will be impacting the variation in SAT, mean SAT scores. What happens here is that takers and rank are highly correlated. And remember, we interpret statistical significance in a context of a multiple linear regression. That means we conclude that the coefficient is not statistically significant given that there are other predictors in a model. Given, for example, that rank, the second predictor, is in a model. So this is why we find that the p-value is large in this context, and this draws our attention to the idea of marginal versus conditional model. If we want to test for overall regression, we can use the F test. The F value is 51.91. The p-value is approximately 0, which means that there is at least one of the predictive variable that has predictive power among the predictive variables we include in a model. If we want to estimate the confidence intervals for the individual regression coefficients, we can use this command line where we need to specify the model, the predictor for which we want to estimate the confidence intervals, and the level if it's different than 0.95. The default for level is 0.95. Here we want a 90% confidence interval, so we specify this to be 0.99. And this is what the confidence interval is estimated, as the estimated coefficients is between -2.3 and 1.3, which means that the interval includes 0, thus it's plausible that the regression coefficient to be 0, given all other predictive variables are in the model. In order to test whether the model with the controlling factor versus the model with the controlling factors plus the other 4 explanatory models are one is better than the other, we can perform the partial F test using the ANOVA command in R. In this command, we specify the 2 models. First is going to be the reduced model, including only the controlling factors, takers and rank. And the other one is going to be the full model, including both the controlling factors and the explanatory factors. And the output provides exactly what we wanted, the partial F value, which is 8.6221, and the P value. So this test, again, will test whether reduced model, where takers and rank are in the model versus the full model, and the F value and the P value are us on the output. Because the P value is approximately 0, it means that we reject the null hypothesis that the coefficients corresponding to the 4 predictors we're adding to the model are 0. So list 1 predictive variable among the 4 improves the predictive power of the model versus the model that doesn't include the 4 predictors. This is the more formal test that we just performed. We want to test whether the coefficients of the 4 predictors when adding to the model are equal to 0. The F statistic is the sum of square regression of the extra sum of square regression by adding the 4 predictors to the model that already has the controlling factors divided by the mean sum of square of errors of the full model. The p-value is the probability that F with 4 and 43 degrees of freedom is greater than F statistic. And we interpret this as the p-value is approximately 0, thus we reject because the p-value is approximately 0, we reject the null hypothesis. We conclude that at least 1 other predictor among the 4 predictors, income, years, public, and expenditure, will be significantly associated to the state average SAT score. In this lesson, we learned how to use our statistical software to implement statistical inference on multiple linear regression. Thank you.